Welcome, truly curious mind, to the deepest, most tranquil layers of the sleepy enigma. Tonight we transcend mere observation. We aim to truly linger in the profound questions of the universe, allowing them to become the gentle hum of our deepest contemplation. We are not just exploring time. We are attempting to wrap our very consciousness around its most intricate weaves, from the fleeting perception of a single moment to the vast, timeless expanse of cosmic existence. It is an enigma that defines our every breath, yet remains stubbornly opaque to our full comprehension. How can something so universally present be so deeply personal, so scientifically elusive, and so philosophically contentious? It is as if time itself is playing a cosmic game of hide-and-seek, revealing just enough to tantalize, but never quite enough to fully surrender its ultimate secret. Before we plunge into these even more intricate layers, take a moment to notice the rhythm of your own breathing, the gentle rise and fall of your chest. Feel the steady beat of your heart, a natural metronome within you. Even as we contemplate the grand sweep of cosmic time, your own internal clock is ticking, marking your unique present moment here in Multan, Punjab, Pakistan, on this Friday morning, June 7th, 2025. This very moment, unique to you, is part of the grand unfolding tapestry we are about to explore. If this journey into the profound soothes your thoughts and gently nudges you towards a deeper understanding, please consider giving this video a like and subscribing. It's a small act that helps this quiet corner of exploration reach other minds seeking calm and cosmic wonder. Now, I truly hope this isn't so captivating that it keeps you awake. But if it does, well, at least you'll have wrestled with some of the universe's most beautiful complexities before finally drifting off. So settle in, release your day's worries, and let's expand. Because somewhere between the blink of an eye and the age of the cosmos lies a story yet more vast, more confounding, and more beautiful than we can possibly imagine. The elasticity of our inner clock, the brain's symphony of subjective moments. Our initial dive into the elasticity of subjective time revealed its curious bends and stretches dictated by attention and emotion. But to truly expand, we must venture into the intricate neurological architecture that underpins this phenomenon and explore the deeper implications for our lived experience. Our perception of time isn't just a quirk, it's fundamental to how our consciousness constructs and navigates reality. At the heart of our brain's internal timekeeping lies not a single monolithic clock, but a complex, distributed network of specialized circuits, each likely optimized for different temporal scales. For millisecond-to-second timing, the ultra-fast precision required for motor control, speech articulation, musical rhythm, or even batting a baseball, regions like the cerebellum, crucial for motor coordination and prediction, the basal ganglia, involved in habit formation, reward and procedural learning, and parts of the parietal cortex, integrating sensory information and spatial awareness, are profoundly involved. The cerebellum particularly is thought to act as a kind of timing chip for precise movements, often utilizing recurrent neural networks that can generate precise intervals. The basal ganglia, part of the cortical basal ganglia thalamic loops, are hypothesized to serve as a sub-second accumulator of neural pulses. These pulses, whether from individual neurons firing rhythmically or synchronized groups of neurons engaged in neural oscillations, brain rhythms like gamma, theta, and alpha waves, form the very raw material of our internal clock. Changes in these neural firing rates, influenced by external stimuli or internal states, can directly alter our perception of time's passage. For instance, faster oscillations might lead to a perception of time speeding up, as more ticks occur in less objective time. For second-to-minute timing, the supplementary motor area, SMA, and the insula, a deep brain region involved in interoception or sensing the body's internal state and emotional processing, are thought to play a critical role. The prevailing pacemaker accumulator model posits that a neural pacemaker generates a steady stream of pulses, which are then collected by an accumulator. The more pulses accumulated, the longer the perceived duration. However, this is no static mechanism. Factors like physiological arousal, e.g., from adrenaline during fear, speeding up the heart rate and other bodily processes, dopamine levels, linked to motivation, reward and novelty, or even body temperature, can directly influence the speed of this pacemaker, making time seem to speed up or slow down. For example, higher dopamine levels are hypothesized to accelerate the pacemaker, leading to a faster perceived passage of time when we're excited or anticipating a reward. Conversely, a lack of novel stimulation during profound boredom might slow down the pulse accumulation process, making each minute feel endless. The claustrum, a thin sheet of neurons deep within the brain, has also been speculatively linked to the integration of multisensory information and possibly consciousness itself, raising questions about its potential role in generating a unified, continuous stream of conscious experience that includes time. The profound impact of attention on temporal perception extends further than simple distraction. When we're performing a cognitively demanding task or are highly absorbed, our brain allocates fewer resources to monitoring the passage of time. This time blindness during deep engagement explains the flow state, where the self-consciousness and the sense of time fade. Conversely, when we are deliberately attending to time, e.g., watching a clock counting seconds, our brain actively engages specialized timing mechanisms, paradoxically making the duration feel longer because we're scrutinizing each tick and building more detailed conscious memories of the interval. This is precisely why a watched pot truly never boils. Beyond these broad effects, our subjective clock is also subject to fascinating perceptual illusions. The Kappa effect. When a series of identical stimuli are presented, the perceived duration between them is longer if the perceived spatial distance between them is greater. You'll perceive two flashes of light as taking longer to travel a longer distance, even if the actual time is the same. The Tau effect, the inverse of the Kappa effect. If the perceived duration between two stimuli is longer, the perceived spatial distance between them also increases. The oddball effect. A single, novel, or unexpected stimulus within a sequence of identical stimuli can cause the perceived duration of the oddball to be dilated, making it seem to last longer. This might be due to increased neural processing or heightened attention dedicated to the novel event. Chronostasis, the stop clock illusion. When you glance at a clock, the second hand might appear to freeze for a moment before resuming its normal tick. This is caused by saccadic suppression, the brain suppressing visual input during rapid eye movements or saccades, and temporal filling in, where the brain fills the perceptual gap with what it expects to see, making the first perceived tick of the second hand seem longer. The role of memory in shaping our temporal landscape is also intricate. Beyond the density of novel experiences in childhood making it seem longer, there's the telescoping effect. Backward telescoping, events feeling more recent than they are, often occurs for positive, salient, or frequently recalled events, as they are repeatedly re-encoded and mentally replayed, making them feel closer. Forward telescoping, events feeling more distant than they are, tends to affect negative, routine, or less frequently accessed memories, which are compressed and thus feel further removed. This suggests our subjective timeline isn't just a passive record, but a fluid narrative, constantly being rewritten and re-edited by our brain's dynamic memory systems. As we age, the subjective acceleration of time is also theorized to be due to a combination of factors. The decreasing proportion of novel experiences, routine sets in, leading to less dense memory encoding, a potential slowing of the internal, biological clock itself, neural processing speeds might decrease, and the sheer volume of existing memories that compress new information, making individual years seem shorter relative to the vastness of accumulated experience. Finally, the cultural and linguistic lenses through which we view time are not mere metaphors. They can deeply shape our cognitive framework and even our philosophical stance on time. For instance, the Aymara language, spoken in the Andes, conceptually places the past in front because it's seen, known, and the future behind because it's unseen, unknown. This is physically reflected in their gestures, where they might point forward when talking about past events. This contrasts sharply with most Western languages, where ahead means future and behind means past. Similarly, in Mandarin Chinese, time can be conceptualized both horizontally, qian, front for past, hao, back for future, and vertically, shang, up for last, jia, down for next, influencing spatial reasoning about temporal events. These linguistic structures, as posited by the Sapir-Whorf hypothesis, suggest that language doesn't just describe reality, but can actively shape our perception of it, including something as fundamental as time. Our temporal experience is thus a remarkably rich multi-layered tapestry woven from precise neural activity, fluctuating emotional states, dynamic memory construction, and deep cultural conditioning. The very now we inhabit is, in essence, a complex emergent property of our conscious mind, our biological tick-tock, the enigmatic orchestration of innate rhythms. Across scales beyond the conscious distortions, our bodies are a symphony of meticulously timed processes, hinting at deep innate temporal mechanisms. This isn't a single monolithic clock, but a distributed network of interconnected oscillators, each operating on slightly different timescales, from the sub-second precision of a tennis swing to the multi-year cycles of human development and even the life and death of individual cells. The most prominent of these is the circadian rhythm, our internal approximately 24-hour master clock. It's primarily housed in the suprachiasmatic nucleus, SCN, of the hypothalamus, a minuscule cluster of neurons no larger than a grain of rice. This SCN is exquisitely sensitive to environmental light cues, particularly blue light, detected by specialized retinal ganglion cells distinct from vision-forming rods and cones. The SCN then orchestrates a complex cascade of molecular and hormonal signals, notably the rhythmic production and release of melatonin from the pineal gland, which induces sleepiness. But the circadian rhythm is far more than a sleep-wake timer. It dictates rhythmic fluctuations in body temperature, blood pressure, hormone secretion, e.g. cortisol, growth hormone, digestive activity, cognitive performance, e.g. attention, memory consolidation, and even cellular regeneration throughout the day. Disruptions to this rhythm, like jet lag, shift work, or sleep deprivation, demonstrate its profound impact, leading to not just fatigue, but also impaired judgment, reduced physical performance, and long-term health issues, subtly impacting our perception of how quickly or slowly time is passing. Beyond the 24-hour circadian cycle, our bodies host a fascinating array of other biological rhythms, ultradian rhythms. These cycles occur more frequently than every 24 hours, often in periods of minutes or a few hours. Examples include the REM-non-REM sleep cycle, approximately 90-110 minutes, the cycle of nasal congestion, nasal cycle, and various hormonal pulses throughout the day. These rhythms demonstrate the brain's internal oscillators at work on shorter timescales. Infradian rhythms. These cycles span periods longer than 24 hours, often weeks or months. The most prominent example is the menstrual cycle in females, approximately 28 days. Seasonal affective disorder, SAD, and changes in metabolic rate in response to seasons also fall into this category. At a more fundamental level, the basis of these biological clocks lies within our cells themselves. Nearly every cell in our body possesses its own molecular clock, driven by complex feedback loops of specific clock genes, like period and cryptochrome, and their protein products. These proteins build up and break down rhythmically over approximately 24 hours, influencing cellular functions. The SCN acts as the master clock, synchronizing these peripheral cellular clocks throughout the body, ensuring internal consistency. Even mitochondria, the powerhouses of our cells, play a role in energy production, and disruptions to mitochondrial function are implicated in aging and various diseases, potentially linking cellular metabolism to an individual's perceived rate of aging and the speed of their internal clock. The inherent inaccuracies in our time estimation stem from the very nature of these biological clocks. Unlike a perfectly precise quartz crystal's unwavering vibration, neural oscillations are subject to neural noise, random fluctuations in neuronal firing, cognitive load, divided attention, stress, and even subtle changes in body temperature or hydration can affect the consistency of these internal beats, leading to errors in estimation. For example, during high-stress situations, an influx of adrenaline and other stress hormones can lead to a perception of slowed time, possibly by enhancing attention and information processing speed, making the internal clock feel faster and thus stretching subjective duration, or by increasing the subjective vividness of memories formed during the event. Conversely, boredom, marked by low arousal and dopamine, might make the internal pacemaker feel slow, drawing out every second. The influence of various neurotransmitter systems is critical. Dopamine, as discussed, influencing pacemaker speed. Acetylcholine, crucial for attention and memory encoding, thus affecting how deeply we process and recall time. Serotonin, modulating mood and perceived speed of external events. And GABA, an inhibitory neurotransmitter crucial for neuronal rhythm and timing. And that ubiquitous, infuriating snooze button? Its temporal trickery is a perfect storm of biological disruption. When you hit snooze, you're repeatedly forcing your brain back into a fragmented liminal state between sleep and wakefulness, known as sleep inertia. Instead of completing full restorative sleep cycles, which typically last 90–110 minutes and cycle through light, deep and REM sleep, you're constantly pulled from deeper stages into light sleep or a disoriented semi-consciousness. This prevents the brain from entering the restorative phases of sleep that reset and optimize cognitive functions. In this disoriented state, the brain's ability to accurately encode and perceive the passage of time is severely impaired. The neural oscillators involved in timing become discombobulated, leading to a profound subjective compression of those fleeting, precious minutes. It's a stark reminder of how exquisitely sensitive and easily influenced our internal temporal mechanisms are to our physiological state and external habits. Ultimately, our brain constructs a subjective experience of time that is intensely personal, adaptive, and often beautifully imprecise. It's a testament to the brain's profound ability to interpret and filter reality, creating a sense of temporality that, while wobbly and wonderful, is undeniably crucial for our navigation and understanding of the world. But it also highlights that objective time, as measured by clocks, is something quite different from our internal embodied experience. The biological reality of time is a fascinating realm where cellular rhythms, neural networks, and chemical messengers conspire to create our uniquely human sense of duration and temporal order. From sundials to atomic precision, humanity's obsessive pursuit of temporal fidelity. If our internal experience of time is a wild, unpredictable river, then humanity's collective efforts to measure it are a magnificent testament to both our ingenuity and an almost comical obsession with control. From the earliest observations of the cosmos to the mind-boggling precision of atomic clocks, we've spent millennia striving to wrangle this invisible, ephemeral force into something we can see, count, and crucially, schedule around. Because while time may wait for no one, humans are incredibly fond of asking it to hold on just a minute. This relentless pursuit reflects a deeper human need to organize, to predict, to communicate, and ultimately to understand our place in the universe. Our story of timekeeping begins in the deep past, when the first clocks weren't intricate devices, but the grand, majestic movements of the sky itself. Our ancient ancestors were expert observers of the heavens, the predictable rising and setting of the sun, the mesmerizing phases of the moon waxing and waning, the slow, rhythmic shifting of the seasons. These were nature's earliest, grandest calendars, requiring no batteries, only keen observation, and a deep innate connection to the natural world. This rhythmic predictability provided the first fundamental framework for human organization, from knowing when to plant and harvest crops to coordinating hunting expeditions and celebrating crucial seasonal rituals, giving structure to otherwise amorphous stretches of duration. The Babylonians, for instance, with their advanced astronomical observations, developed a sexagesimal, base 60 number system for their calculations, a legacy that endures today in our division of circles, 360 degrees, hours, 60 minutes, and minutes, 60 seconds. The ancient Egyptians, a civilization obsessed with order and cosmic cycles, were among the first to formalize timekeeping around 1500 BCE. They constructed towering obelisks and later developed smaller shadow clocks that acted as portable sundials, their sharply defined shadows marking the passage of daylight. They even developed the Merkiet, a stellar clock for night use, using 2 plumb bobs and a sighting slit to align with specific stars, allowing them to measure time by observing stellar transits across the meridian. However, a significant limitation was that the lengths of these hours changed with the seasons. An hour in summer was considerably longer than one in winter due to the varying arc of the sun, and they were utterly useless on cloudy days. Still, it was a profound leap, providing a degree of temporal organization sufficient for farming, religious ceremonies, and structuring early society. To overcome the limitations of sundials, water clocks, or clepsydrae, emerged as the next ingenious innovation. These devices, utilized by the Egyptians, Greeks, Chinese, and Romans, measured time by the steady, regulated flow of water from one vessel to another. They were a significant upgrade, consistent in their measurement, though still affected by temperature, water viscosity, and pressure changes as the reservoir emptied, and crucially capable of working at night or on overcast days. Early examples include the elaborate clepsydra at the Tower of the Winds in Athens, incorporating intricate mechanisms. Some were surprisingly complex, featuring gears, floats, and intricate figures that chimed the hours or even rang bells, serving as early automatons. Meanwhile, in distant Mesoamerica, the Maya civilization developed astonishingly intricate calendar systems, such as the long count calendar, which tracked lunar and solar cycles with a level of accuracy that often surpassed their European counterparts of the same era. Their complex cycles could measure spans of time covering thousands of years, reflecting a profound understanding of celestial mechanics and the cyclical nature of time, often tying time to grand cosmic narratives. Back in Europe, it wasn't until the High Middle Ages, around the 13th-14th centuries, that mechanical clocks began their slow, deliberate tick-tock into history. At first, these were colossal, unwieldy iron contraptions installed in church towers and monasteries. They lacked faces or hands as we know them. Instead, they primarily served a monastic purpose, simply ringing bells at regular intervals to mark the canonical hours, reminding monks when to pray. One might say monks were the world's first alarm clock users, though likely far more serene about it than most of us at 6 a.m. These early tower clocks, often driven by falling weights, were less about telling precise time and more about providing a communal, audible sense of temporal order, standardizing daily rhythms across towns and facilitating the coordination of public life. A monumental leap forward in mechanical timekeeping came in the 14th century with the invention of the verge, escapement and foliot balance. This ingenious piece of engineering provided a mechanism to convert the continuous falling motion of a weight into a precise oscillating motion, allowing for a controlled, regular release of energy. The foliot balance, a simple bar with weights, rocked back and forth, engaging and disengaging the escapement mechanism to regulate the descent of the weight. This was the crucial regulatory component that enabled the development of truly smaller, more reliable mechanical clocks. Eventually, inventive clockmakers added dials and hands, so people could actually see the time, not just hear it tolled from a distant bell tower. From this point, the pace of innovation began to tick faster, driven by a growing societal need for more precise timing in commerce, industry, and, crucially, navigation. The 17th century ushered in the era of the pendulum clock, thanks to the brilliant Dutch scientist Christian Huygens. His work was inspired by Galileo Galilei's earlier observations, around 1583, of a swinging lamp in Pisa Cathedral, where Galileo noted the isochronism of the pendulum, its property of taking the same amount of time to complete each swing, regardless of the size of the arc within limits. Huygens, building on this theoretical insight, engineered the first practical pendulum clock in 1656, Pendulum clocks were a revelation, accurate to within a minute a day, a staggering improvement over earlier mechanical designs that could drift by hours. If time was a wild, untamed horse, the pendulum was the sturdy, reliable saddle that finally allowed us to ride it with confidence and precision. This breakthrough profoundly impacted scientific research, allowing for more accurate astronomical observations, enabling the rise of precision instruments, and facilitating experiments that required accurate temporal measurements, pushing the boundaries of scientific inquiry. However, the high seas presented a formidable challenge. During the Age of Exploration, 15th to 18th centuries, the desperate need for even more precise timekeeping became critically urgent. Sailors could easily determine their latitude, north-north or south-south position, from the stars, but calculating longitude, east-west position, was a monumental problem. It required knowing the exact time at a fixed reference point, like Greenwich, England while at sea, and comparing it to local apparent noon. A clock that could keep accurate time over months of rolling, pitching, temperature extremes and humidity was desperately needed, and the British government offered a colossal prize for it, the Longitude Act of 1714. Enter John Harrison, an English carpenter and self-taught clockmaker, who dedicated over 4 decades of his life to inventing marine chronometers, ultra-precise clocks specifically designed to survive the harsh conditions of a ship at sea. His fourth model, the magnificent H4, completed in 1759, a masterpiece of micro-engineering and ingenuity, incorporating bimetallic strips for temperature compensation, constant force escapements, and frictionless bearings, finally solved the longitude problem, changing global navigation forever and earning him, after much bureaucratic resistance, his belated but well-deserved place in history. The 19th century saw further refinements, such as the gridiron pendulum, using different metals to compensate for thermal expansion. The 20th century then ushered in the age of quartz timekeeping. Quartz crystal oscillators, first developed in the 1920s, revolutionized timekeeping once again. The principle behind them is the piezoelectric effect. When an electric current is applied to a quartz crystal, it vibrates at an incredibly stable and precise frequency, often millions of times per second, e.g. 32,768 Hz for common watches. These consistent high-frequency vibrations could then be used to drive electronic circuits that count the oscillations and translate them into accurate timekeeping. Suddenly, clocks and watches could be cheap, highly portable, mass-produced, and accurate enough to literally keep the trains running on time, or at least give us no excuse when they didn't. This marked a profound shift from mechanical dominance to electronic precision and miniaturization. But even the remarkable precision of quartz has its limits. If you want to know the most accurate time on Earth, you must turn to atomic clocks. Following early attempts with ammonia Mausers, the first successful atomic clock, based on the cesium atom, was built in the 1950s. Atomic clocks measure time using the natural, incredibly stable and reproducible quantum transitions of atoms, typically cesium-133 or rubidium. A cesium-133 atom, for instance, is excited by microwave radiation, and when it transitions between 2 specific hyperfine energy levels, it oscillates at an exact frequency of 9,192,631,770 cycles per second. That precise number isn't just arbitrary trivia. It is the official definition of a second. 1 second, 9,192,631,770 cycles, according to the International System of Units, SI, a definition adopted in 1967 by the International Bureau of Weights and Measures, BIPM. These clocks are so staggeringly precise that the best ones would lose or gain less than 1 second in over 300 million years. This astonishing accuracy even necessitates the occasional addition of a leap second, announced by the International Earth Rotation and Reference System Service, IERS, to keep International Atomic Time, TAI, synchronized with Universal Time, UT1, which is based on the Earth's slightly irregular rotation. Today, atomic clocks are the silent, invisible backbone of our entire modern technological world. They are used to synchronize everything from GPS satellites, which rely on picosecond precision, to pinpoint your location within meters, to the intricate networks of the internet, global telecommunications, and high-speed financial trading systems. They are critical for fundamental physics experiments, deep space communication, and even the precise timing needed for gravitational wave observatories. The latest frontier, optical atomic clocks, which use higher frequency transitions in atoms, like strontium or ytterbium, operating in the optical rather than microwave spectrum, promise even greater precision, potentially losing less than a second in tens of billions of years, opening new avenues for testing fundamental physics, searching for dark matter, and even exploring the nature of gravity itself at unprecedented scales. Time, once measured by dripping water and fleeting sun shadows, now depends on atoms flipping like microscopic metronomes in high-tech vaults, a profound testament to humanity's relentless, almost obsessive, pursuit of precision and control over the elusive current of time. This relentless pursuit of precision in timekeeping reflects a deeper human drive. It's about more than just telling the hour. It's about control over our environment, coordination of complex activities, communication across vast distances, and ultimately, a fundamental desire to understand the underlying rhythm of the universe itself. We transitioned from natural time, tied to celestial cycles, to artificial time, clocks we build, giving us mastery over our schedules, but perhaps also subtly distancing us from the organic flow of the cosmos. Yet even with all this incredible precision, time still feels strangely, wonderfully personal. We can divide it into hours, minutes, and seconds. We can watch it scroll by on digital screens. But no matter how finely we slice it, we each live it differently. So we measure, we synchronize, we analyze, but the profound mystery of what time is continues to beckon, promising secrets yet untold. Newton's absolute time, the grand, unchanging stage, and its philosophical echoes for much of human history. As we've seen, time was a local affair, tied to the rhythms of nature and the convenience of community. But the intellectual ferment of the Enlightenment brought with it a profound shift in perspective, a drive to uncover universal laws that governed not just our small corner of the earth, but the entire cosmos. At the forefront of this revolution stood Isaac Newton, a towering intellect of the 17th century, whose work laid the very foundation for what we now call classical mechanics. Newton didn't just describe the world, he sought to pin it down with rigorous mathematical precision. In his monumental work, Principia Mathematica, 1687, he presented a vision of the universe as a grand, predictable machine, operating according to immutable laws. Central to this vision were the concepts of absolute space and absolute time. For Newton, these were not merely conceptual tools but fundamental, independent entities, existing entirely apart from the matter and events within them. Newton conceived of absolute time as a uniform, self-sufficient entity that flowed equitably and independently of anything external. In his own words, absolute, true, and mathematical time of itself and from its own nature flows equitably without regard to anything external, and by another name is called duration. This means that time was like a vast, unseen river whose current flowed at a perfectly steady, unvarying pace, unaffected by whether anyone was watching, counting, or even existing. It was a universal, fixed clock, ticking identically for every observer, everywhere in the universe. If you could somehow step outside the universe, you would still observe this time flowing, providing a consistent, unchanging backdrop against which all events unfolded. This concept of absolute time, alongside absolute space, was the philosophical and mathematical cornerstone of Newton's entire system of physics. His three laws of motion and his law of universal gravitation explicitly assumed this universal independent temporal framework. These laws allowed scientists to describe motion in precise mathematical terms, to calculate the exact trajectories of planets, the precise swing of a pendulum, or the predictable arc of a cannonball. The beauty of this framework was its consistency. If an event happened at a specific time in one location, an observer elsewhere moving at a different speed would still agree on the exact time of that event. This made the universe wonderfully deterministic and mechanistic, running like, well, clockwork. Every particle's future, given its current state, was uniquely determined. This vision profoundly shaped the scientific worldview for centuries. However, this idea was not without its philosophical challenges, even in Newton's era. The brilliant German philosopher and mathematician Gottfried Wilhelm Leibniz, Newton's intellectual rival and co-inventor of calculus, vehemently disagreed with the notion of absolute time and space. Their famous Leibniz-Clark correspondence, 1715-1716, a series of letters exchanged between Leibniz and Newton's champion Samuel Clarke, laid bare this profound philosophical divide. Leibniz argued for a relational view of time. For him, time was not a pre-existing container or a flowing entity. Rather, it was simply the order of successive events. Without events, he argued, there is no time. To illustrate, consider the empty universe thought experiment. If there were absolutely nothing in the universe, no matter, no energy, no events, would time still flow? For Newton, yes, it would, as an independent entity. For Leibniz, no, because there would be nothing to mark its passage, no relations between things to define its existence. Time, to Leibniz, only has meaning when things actually happen in sequence, providing a basis for comparison. His argument was rooted in the principle of sufficient reason, stating that nothing exists without a reason why it exists, and no truth is true without a reason why it is true. To Leibniz, absolute space and time violated this principle, as there would be no sufficient reason for a particular particle to be in one absolute position rather than another, or for the universe to have begun at one absolute moment rather than another. This profound philosophical debate highlighted the fundamental assumptions embedded in Newton's physics. Despite its philosophical critiques, Newton's model's practical success largely overshadowed the conceptual challenges for centuries. It was the bedrock of Galilean invariance, meaning that the laws of mechanics were the same in all inertial frames of reference. This principle worked perfectly for describing macroscopic motion here on Earth and throughout the solar system. But cracks began to appear in the Newtonian edifice by the late 19th century, particularly with advancements in the study of electromagnetism. James Clerk Maxwell's equations, 1860s, unified electricity, magnetism, and light, showing that light was an electromagnetic wave that traveled at a constant speed, c, regardless of the motion of its source or observer. This was a profound anomaly for Newtonian physics. If light were like sound, its speed should be relative to the medium it travels through, like air. Scientists, clinging to the idea of an absolute reference frame, posited a hypothetical, invisible medium called the luminiferous ether as the ubiquitous medium for light waves to propagate. This ether was assumed to fill all space, and Earth's motion through it should produce a detectable ether wind. Countless experiments were designed to detect this ether and measure Earth's speed relative to it. The most famous, the Michelson-Morley experiment of 1887, definitively failed to detect any such ether, demonstrating that the speed of light truly was constant for all observers, regardless of their relative motion. This was a direct contradiction of the core principles of absolute time and relative velocities inherent in Newtonian mechanics, creating a fundamental crisis in physics that could not be resolved within the Newtonian framework. This lingering paradox, this persistent inconsistency, set the stage for a young patent clerk named Albert Einstein to revolutionize our understanding of reality, replacing Newton's solid, unchanging stage with a dynamic, interconnected fabric where time was no longer a universal constant, but a deeply personal relative dimension. But even as we move beyond Newton's framework, it's crucial to acknowledge the immense power and clarity his vision provided for hundreds of years, shaping our intuitive understanding of the cosmos and laying the groundwork for all that came after. Newton's time, though proven incomplete, remains incredibly useful for most everyday scenarios, providing a reliable framework for our lives and the basis for much of classical engineering and technology. Einstein's wibbly-wobbly trampoline of time, where reality is a dynamic, Four-dimensional dance, if Isaac Newton laid out time as a majestic, universally flowing river, always constant and uniform for everyone, then Albert Einstein didn't just divert the river, he revealed it to be an integral part of a vast, dynamic, four-dimensional ocean, its flow dictated by mass and motion. He essentially showed that our understanding of time was merely a convenient simplification of a much richer, more interconnected reality. In the early 20th century, a young, audacious Einstein, then a humble patent clerk, began to unveil a series of ideas so radical they fundamentally reshaped our understanding of the universe. His theories of relativity, special relativity 1905 and general relativity 1915, didn't just describe the universe, they redefined the very concepts of space and time themselves. Let's first delve deeper into special relativity, a theory born when Einstein was just 26, from his contemplation of light and motion. It's built upon two deceptively simple, yet profoundly revolutionary postulates that emerged from the crisis in classical physics regarding light. The principle of relativity. The laws of physics are the same for all observers in inertial frames of reference, i.e. those moving at a constant velocity without acceleration. There is no absolute rest frame to which all motion can be compared. The constancy of the speed of light. The speed of light in a vacuum, (MIS), is the same for all inertial observers, regardless of their motion or the motion of the light source. This was the brilliant, daring leap that resolved the Michelson-Morley experiment's perplexing results. These two postulates, when taken together, force extraordinary consequences on our understanding of time and space. Since light speed is constant for everyone, if you're moving relative to someone else, you must disagree on measurements of distance and duration to maintain that constant speed of light. This isn't arbitrary. It's precisely described by the Lorentz transformations, a set of equations that mathematically describe how measurements of space and time change between different inertial frames. These transformations demonstrate that space and time are not independent, but inextricably linked, leading to the famous effects. Relativity of simultaneity. Events that are simultaneous for one observer are not necessarily simultaneous for another. Observer moving relative to the first. Imagine a light pulse emitted from the center of a fast-moving train car. To an observer on the train, the pulse hits the front and back of the car simultaneously, but to a stationary observer on the platform, because the car is moving, the light ray has less distance to travel to the back of the car and more to the front. Since light's speed is constant, the stationary observer sees the light hit the back of the car before it hits the front. There is no universal now. The very concept of simultaneity becomes relative to the observer's frame of reference. Time dilation, the most famous consequence. Time truly passes more slowly for an object in motion relative to an observer at rest. To grasp this intuitively, consider a light clock, where a photon bounces between two mirrors. If the clock is stationary, the photon travels straight up and down. If the clock is moving sideways relative to you, the photon must travel a longer diagonal path to hit the mirrors. Since the speed of light, c, is constant for both observers, for the moving photon to cover that longer diagonal distance in the same time relative to itself, more time must objectively pass for the stationary observer to account for the longer path. This means the moving clock appears to tick slower. This isn't just an illusion, it's a measurable physical reality. For instance, muons, unstable subatomic particles created in Earth's upper atmosphere, have an extremely short lifespan, about 2.2 microseconds. Traveling at near-light speeds, time dilation extends their effective lifespan by factors of 10 or more, allowing them to reach the Earth's surface in significant numbers, which wouldn't happen if their decay time were absolute. This effect is also precisely observed in particle accelerators, where short-lived particles exist for far longer than their at-rest lifetime would predict. Length. Contraction. Similarly, objects moving at high speeds appear to contract or shorten in the direction of their motion, as observed by a stationary observer. This means that a space traveler moving at near-light speeds would find distances along their direction of travel compressed. Relativistic mass, historical concept leading to EMC2. While modern physics tends to describe these effects more precisely, using energy-momentum 4 vectors, early interpretations of special relativity also led to the idea that an object's mass appears to increase as it approaches the speed of light, making it infinitely difficult to accelerate to see. This concept, however, is now typically folded into the more encompassing understanding of mass-energy equivalence, E/mc2, which fundamentally reveals the deep interconnectedness of mass and energy, showing that mass is a concentrated form of energy and vice versa. It demonstrated that energy, mass, space, and time are not separate entities but different facets of a unified reality. The famous twin paradox elegantly illustrates time dilation. One twin takes a relativistic journey into space, while the other remains on Earth. When the traveling twin returns, they are genuinely younger than their earthbound sibling. The paradox is resolved by recognizing that the traveling twin experiences acceleration and deceleration, changing inertial frames and undergoing turns, which breaks the symmetry of the scenario, making the time dilation asymmetric. Building. Upon special relativity, Einstein unveiled his masterpiece general relativity in 1915. This theory transcended special relativity by incorporating gravity and acceleration. Einstein's revolutionary insight was to realize that gravity is not a mysterious force pulling objects together, as Newton conceived. Instead, he proposed the equivalence principle. Acceleration is indistinguishable from gravity locally. This led him to the breathtaking conclusion that gravity is simply the curvature of space-time itself, caused by the presence of mass and energy. Imagine space-time not as an empty, rigid stage, but as a stretched, flexible trampoline. Placing a heavy object, like a star or a planet, on this trampoline causes a dent or curvature. Other objects, like light rays or smaller planets, don't feel a force pulling them. Instead, they simply follow the shortest possible path along the curves and dents in this space-time fabric. This is why planets orbit stars and light bends around massive objects. Mathematically, this curvature is described by the metric tensor, a complex mathematical object that tells us how to measure distances and durations in curved space-time. The profound consequence for time is gravitational time dilation. Time passes more slowly in stronger gravitational fields. The closer you are to a massive object and thus the deeper you are in its gravitational well, the dent in space-time, the slower your clock will tick, relative to someone in a weaker gravitational field farther away. This too is not merely theoretical. The Pound-Rebka experiment, 1959, famously confirmed this by showing that gamma rays traveling upwards in Earth's gravity experienced a tiny frequency shift, a change in their ticking rate, as they escaped the stronger gravitational field near the ground. For us, this means that your head, being slightly farther from Earth's center of mass, is aging infinitesimally faster than your feet. The most critical real-world application of both special and general relativistic time dilation is the Global Positioning System, GPS. GPS satellites orbit Earth at high speeds, around 14,000 km/h, and at high altitudes, about 20,200 km. Due to their high speed, special relativity predicts their clocks should run slower by about 7 microseconds per day. However, because they are farther from Earth's strong gravitational field, general relativity predicts their clocks should run faster, by about 45 microseconds per day. The net effect is that satellite clocks gain about 38 microseconds, Jozazo 38 seconds, per day, relative to clocks on Earth. This tiny discrepancy is enormous for GPS accuracy. If left uncorrected, your phone's location would be off by several kilometers within minutes, rendering the system useless. Every GPS receiver precisely accounts for these relativistic effects, confirming Einstein's once radical predictions daily. Einstein's work led to the revolutionary concept of space-time, first formally proposed by his former teacher, Hermann Minkowski. Events are no longer just defined by 3 spatial coordinates and a separate, independent time coordinate. Instead, they exist within this unified 4-dimensional space-time continuum, where space and time are inextricably linked and warped together. This is often visualized using a light cone, which represents the paths that light, and therefore anything that can influence us or be influenced by us, can take through space-time from a given event. It rigidly defines causality. Events inside. The past light cone can influence the present, and events inside the future light cone can be influenced by the present. This profound insight means that your time, the pace at which you experience the universe, the rate at which your personal clock ticks, depends profoundly on where you are and how you move within this dynamic interacting fabric. It's a deeply strange idea, yet also incredibly beautiful, revealing a universe far more interconnected and fluid than previously imagined. Time is no longer absolute, it is relative, a local phenomenon influenced by its cosmic environment. General. Relativity also predicted other mind-boggling phenomena. Gravitational lensing, the bending of light around massive objects causing distant galaxies to appear distorted or multiplied. Black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape. At the event horizon of a black hole, time dilation becomes infinite, meaning time effectively stops for an outside observer as an object approaches the horizon. Gravitational waves, ripples in the fabric of space-time, predicted by Einstein a century ago, and first directly detected in 2015 by the LIGO experiment. These waves propagate at the speed of light, carrying energy and confirming that space-time is not static, but a dynamic, undulating medium. Einstein's work didn't just rewrite physics textbooks, it fundamentally changed how we see reality itself. Time is not a fixed, independent background upon which events unfold. It's an active, integral part of the cosmic dance, shifting and flowing with the rhythm of matter and energy. This raises deep philosophical questions about presentism, only the present moment is real, versus eternalism, past, present, and future are equally real, coexisting in a block universe of space-time. If there is no universal now and all, events are just points in a four-dimensional manifold. Our perception of time's flow might be an illusion of our consciousness. So next time someone tells you they're running out of time, you can gently remind them, actually time is running out differently depending on your velocity through space-time and your proximity to gravitational mass. Perhaps you should try orbiting a black hole for a while to conserve it. Then perhaps offer a knowing smile and prepare to gracefully duck the arrow of time, entropy's inexorable march, and the universe's grand destiny. Let's play a truly mind-bending mental game, one that highlights a profound mystery at the heart of time itself. Imagine just for a moment that you wake up one morning and find everything running perfectly backwards. Your morning toast leaps out of your mouth and lands perfectly buttered on a plate, its crispness returning as if never touched. Your tea, instead of cooling, grows hotter as you drink it, steam magically condensing into the mug. Raindrops fly gracefully upward into the sky, merging seamlessly with the clouds. A shattered vase spontaneously reassembles itself from fragments on the floor. Strange, certainly. Impossible, according to our everyday experience. But impossible, according to the fundamental laws of physics? Surprisingly, no, not exactly. This odd, almost whimsical thought experiment leads us to one of the most intriguing and at times unsettling questions in all of science. Why does time seem to have a relentless, undeniable direction? This is the heart of the arrow of time. In most of the fundamental laws of physics, from Newton's elegant laws of motion to Einstein's relativity, and even the intricate equations of quantum mechanics, time doesn't inherently possess a preferred direction. These laws are time-symmetric. They work just as well backwards as they do forwards. If you were to film two billiard balls colliding on a table and then play the footage in reverse, the physics would still perfectly check out. No alarms would go off in the equations, no physical laws would be violated. The fundamental interactions at the microscopic level are reversible. And yet, in our everyday macroscopic lives, time feels like an unidirectional one-way street, an unstoppable current dragging us relentlessly forward. Eggs break, but never spontaneously unbreak and reform. Paper burns into ash, but ashes never spontaneously reassemble into intact books. We possess vivid memories of the past, but we have no direct knowledge or memory of the future. So, why this profound disconnect? Why does time at our human scale march inexorably from yesterday to tomorrow, never pausing, never reversing? Enter the crucial concept of the arrow of time. This arrow is a powerful metaphor used to describe the singular one-way direction in which time appears to flow, from the past through the present irrevocably into the future. And the key to understanding this arrow lies in one of the most important and occasionally untidy laws of physics, the second law of thermodynamics. This fundamental law tells us that in any closed system, a system that doesn't exchange matter or energy with its surroundings, and for all practical purposes the universe itself can be considered one, entropy always increases or stays the same over time. It never decreases. What exactly is entropy? Simply put, it's a measure of disorder, randomness, or the number of possible microscopic arrangements, microstates, that correspond to a given macroscopic state, macrostate. A highly ordered state, like an intact glass, has very few ways for its molecules to be arranged. A disordered state, like a shattered glass, has countless ways for its fragments and molecules to be arranged, making it far more statistically probable. In other words, the universe has an inherent, overwhelming, statistical tendency to go from tidy to messy, from ordered to chaotic, from states of low probability to states of high probability. You can easily scramble an egg, distributing its components into a disordered state, where there are countless ways the molecules can be arranged, but you simply cannot unscramble it. Why? Not because it's forbidden by fundamental particle physics, but because the probability of all those millions of molecules spontaneously reassembling into their original ordered state is so astronomically small as to be practically impossible within the age of the universe. Your perfectly organized desk will naturally become cluttered unless you actively exert effort to organize it, which involves increasing entropy elsewhere, like the energy you expend. Socks, famously, will always disappear mysteriously from your laundry, but they never ever spontaneously reappear in matching pairs. This universal tendency toward increasing entropy is precisely what gives time its arrow. It's why we experience events in a particular, irreversible sequence. The low entropy, more ordered past naturally transitions into the high entropy, more disordered future. And there's no reversing the flow, no matter how much we might wish for it. The fundamental laws of physics might be reversible in theory, but the overwhelming force of probability, driven by entropy, stands firmly in the way of time reversal in our macroscopic world. This concept is beautifully formalized by Boltzmann's H-theorem in statistical mechanics, which connects the macroscopic increase in entropy to the microscopic probabilities of particle arrangements. This leads us to one of the most intriguing and slightly unsettling questions in modern cosmology. Why was the universe in such an incredibly low entropy, highly ordered state to begin with? After all, if entropy must always increase, there had to be a starting point, a kind of cosmic neat and tidy drawer from which all this magnificent, ever-increasing disorder could unfurl. The prevailing cosmological model, the Big Bang theory, suggests that the early universe was astonishingly uniform, smooth, and incredibly hot and dense, a state of extremely low entropy. Over billions of years, gravity and cosmic expansion did their profound work, leading to the formation of galaxies, stars, and planets, and generally a more chaotic high-entropy universe. But why it started in such an exquisitely ordered state remains one of physics's biggest, most tantalizing open mysteries. Various theoretical approaches attempt to address this. Cosmic inflation theory. This posits a period of extremely rapid, exponential expansion in the very early universe, which could have smoothed out any initial irregularities, leading to a remarkably uniform and low entropy state necessary for the growth of structure we observe today. Multiverse hypotheses. Some theories suggest our universe is just one of many in a vast multiverse, each with different initial conditions. Perhaps in some universes, entropy might decrease. But we could only exist in a universe where entropy increases, providing the necessary conditions for complex structures, like us, to form and evolve. The past hypothesis. This less explanatory, but still viable idea, championed by cosmologist Sean Carroll, simply states that the initial state of the universe, the Big Bang, was, by definition, a state of incredibly low entropy. It's a fundamental initial condition, rather than something to be derived from deeper principles. Roger Penrose's Weyl curvature hypothesis. This proposes that the Big Bang was characterized by a very low Weyl curvature, a measure of gravitational, tidal forces and the intrinsic curvature of spacetime, which contributes to gravity's entropy, leading to an extremely ordered initial state. It's important to recognize that there are several reinforcing arrows of time, each pointing in the same unwavering direction, all fundamentally intertwined with entropy. The thermodynamic arrow. Entropy arrow. This is the most fundamental driving force. It dictates that systems move from order to disorder. All irreversible processes, from your coffee cooling to a star burning out, are manifestations of this arrow. It's the ultimate arbiter of which way time flows. The radiative arrow. Electromagnetic. Waves like light radio waves or heat radiation always expand outwards from their source, never spontaneously converging inwards to a single point. This too is an entropic process. A diffused wave is more disordered than a concentrated one. If light converged, we could see future events. The psychological cognitive arrow. We remember the past, but not the future. This isn't just a mental quirk. It's deeply tied to physics. Memories require physical processes in the brain that leave behind traces, like new neural connections or chemical changes. These memory formation processes are inherently entropy increasing. You can't remember the future because it simply hasn't happened yet, and thus no physical traces have been laid down for your brain to recall. This arrow is fundamental to our subjective experience of time. The causal arrow. Causes always precede effects. You flip a light switch and then the light comes on. You don't turn on a light and then decide to flip the switch. This concept of strict temporal order is tied to the second law, as backward causation would fundamentally violate the principle of increasing entropy. It's the bedrock of our understanding of how events unfold. The cosmological arrow, expansion. Arrow. This refers to the ongoing expansion of the universe itself. The fact that galaxies are moving away from each other, space is continually stretching, and everything is cooling down over vast periods gives a profound sense of direction to the cosmos. This expansion helps the universe move to higher entropy states, more room for particles to spread out. The ultimate fate of the universe, whether it ends in a big crunch, contraction, a big freeze, heat death, maximum entropy and thermal equilibrium, or a big rip, accelerated expansion tearing everything apart, has profound implications for the cosmological arrow and the very meaning of time in the far future. If the universe were to contract, would the arrow of time reverse? This remains a captivating theoretical playground. The quantum arrow, the process of quantum measurement, where a superposition of possibilities collapses into a single definite outcome, is often considered fundamentally irreversible. This irreversible step in quantum mechanics might contribute to the arrow of time, though its exact role is still debated. The black hole. Arrow. Black holes, with their one-way event horizons, create a profound arrow of time. Anything that crosses the event horizon can never escape, and information about it seems to be lost. The black hole information paradox, representing an irreversible process that increases the entropy of the universe. It's profoundly comforting, in a way that these fundamental arrows, thermodynamic, radiative, psychological, causal, cosmological, and even quantum and black hole, all align. They all point in the same direction, providing a deep coherence to our experience of reality. It suggests that time isn't just a random illusion or an arbitrary label, but something deeply woven into the very structure of reality itself, a direction carved by the inevitable flow of energy, the relentless march of disorder, and the gentle, vast spreading out of everything from a once exquisitely tidy beginning. Yet despite all this profound understanding, not everyone is convinced that time, as we experience it, is fundamental in the deepest sense. Some physicists argue that the arrow of time is an emergent phenomenon, something that arises only when complex systems like us, with our specific ways of perceiving and interacting, observe simpler ones like tea cooling or egg scrambling. In some interpretations of quantum mechanics, time is just another parameter, like length or mass. Not a dynamic force, not a flowing river, but merely a label for different states of the universe. The universe doesn't inherently feel time, rather we feel time, because of the way our consciousness and the macroscopic world interact with these underlying principles. And that's the curious, enduring paradox. No matter how deeply we dig into entropy, probability, or the most intricate equations, time continues to be both incredibly real in our experience and maddeningly elusive in its fundamental nature. It's something we ride like an inescapable current, yet we can never quite step outside of it to view it objectively. We don't know what's ahead, we can't physically go back, and yet we live our lives by its rhythm, comforted by the unwavering fact that the future, however uncertain, is always on its way. So the next time you feel like time is slipping away, remember, it's not truly lost. It's just following the one rule it's truly good at, moving forward, increasing entropy, and leaving a whimsical trail of mismatched socks and empty teacups behind. Quantum time. The universe's jazz improvisation, where the clock gets wobbly and the future blurs. If classical physics, with its predictable deterministic laws, treats time as a dependable train schedule, always on track, ticking along steadily, allowing for precise arrivals and departures, then quantum mechanics treats it more like a wild, spontaneous jazz improvisation. It's flexible, profoundly mysterious, sometimes wonderfully dissonant, and just when you think you understand what's going on, it throws you a cat in a box and asks you to consider whether it's simultaneously both alive and dead. Welcome to the quantum world, where our everyday notions of reality get deliciously fuzzy, and time itself becomes more of a polite suggestion than a fixed, unyielding rule. In the classical universe, the one we intuitively experience, you can point to an object and confidently say, it's right there doing that specific thing at this exact moment. Everything has a definite position and a definite momentum. But in the quantum realm, the realm of the incredibly small electrons, photons, atoms, particles, don't have neat, definite positions or precise speeds until you actually observe them. Instead, they exist in a cloud of probabilities, a bewildering state of superposition, where they can be in multiple places or possess multiple properties simultaneously. And if even fundamental properties like position and speed are fuzzy, what does that profoundly strange reality imply for time itself? The very when of an event becomes entangled with the what and where. This is where things get truly mind-bending. In some quantum theories, time isn't a continuous, smoothly flowing river that simply carries particles from one moment to the next. Instead, it might be more akin to a series of discrete jumps or clicks, like individual frames in a cosmic movie reel, the smallest indivisible units of time, sometimes hypothesized as Planck time, 5.39 seconds. This idea of quantized time, while highly speculative and not yet confirmed by experiment, suggests that the universe isn't smoothly evolving through continuous moments. It's updating itself in tiny, fundamental increments. This profoundly challenges our most ingrained assumptions about the continuity of time, suggesting that time might be a granular quantity, just like energy or matter. One of the most intriguing and central aspects of quantum mechanics is its inherent uncertainty. Heisenberg's uncertainty principle famously tells us that you cannot precisely know both a particle's exact position and its exact momentum, its speed and direction, at the very same time. But there's also a similar, equally profound uncertainty, relation involving energy, dE, and time, dt, dA dt2, where is the reduced Planck constant. This principle suggests that for extremely short periods, a quantum system can borrow a bit of energy, even if it temporarily violates conservation laws, as long as it pays it back very quickly within that brief temporal window. This bizarre, fleeting wiggle room allows for the constant, spontaneous creation of virtual particles that pop into and out of existence in seemingly empty space, like tiny, ephemeral bubbles in the cosmic foam. These quantum fluctuations imply that time itself might not be as fixed or as rigidly linear as we perceive it on our macroscopic scale, suggesting a quantum foam of space-time at the smallest scales where time itself might be subject to fluctuations. This quantum borrowing of energy also plays a role in the vacuum energy that contributes to the expansion of the universe. Even stranger, in some cutting-edge quantum experiments, the order of events can become fundamentally uncertain or even appear to depend on how you measure them. Imagine an experiment where event A could potentially happen before event B, or B could happen before A. In the quantum world, sometimes both sequences can exist simultaneously in a superposition, or the very act of observation or measurement can decisively determine the actual sequence of events. This mind-boggling phenomenon is known as indefinite causal order, ICO, and it directly challenges our most basic intuition about cause and effect and the unwavering progression of time. It's like the universe hasn't quite decided which way to play the movie until you hit play and force it to pick a sequence. While currently only demonstrated in highly controlled quantum experiments, ICO has profound implications for quantum information processing, quantum computing, potentially enabling more efficient algorithms, and even the very foundations of logic and causality. Another cornerstone concept that deliciously blurs the lines of time is quantum entanglement. When two or more particles become entangled, they are linked in such an intimate way that measuring a property of one instantly seems to influence the other, no matter how vast the distance separating them. This spooky action at a distance, as Einstein famously called it, appears to imply a kind of instantaneous communication that could defy the traditional flow of time and the cosmic speed limit of light. However, it's crucial to understand that while eerie entanglement cannot be used to transmit actual information faster than light, so it doesn't violate the principles of relativity or create grand paradoxes. But it does undeniably suggest a deep, non-local connection woven into the very fabric of reality that profoundly challenges our conventional, discrete, and separated understanding of events in time. It hints at a universe where connections are deeper than mere sequential cause and effect, where events are less about when and more about how correlated. Perhaps the most profound and audacious challenge to our understanding of time in the quantum realm comes from the ongoing, arduous search for a unified theory of everything, often called quantum gravity. Both general relativity, which magnificently describes gravity and the large-scale structure of space-time, and quantum mechanics, which precisely describes the world of the very small, are incredibly successful theories in their respective domains. However, they famously do not play well together. They are fundamentally incompatible at extreme scales, like inside a black hole or at the moment of the Big Bang. When physicists attempt to mathematically combine them, time itself often seems to disappear from the most fundamental equations. For example, in the Wheeler-DeWitt equation, which aims to describe the wave function of the entire universe, the time variable completely vanishes, leading to what is famously known as the problem of time in quantum gravity. This problem of time has led to several radical philosophical and scientific ideas about time's true nature at its deepest level. Timelessness, block universe. Some interpretations, particularly those influenced by a deterministic view of quantum mechanics, propose that the universe is fundamentally timeless. What we perceive as time is merely an illusion, a static block universe where all moments, past, present, and future, coexist simultaneously, laid out like frames in a film reel. Our perception of flow, or now, is an artifact of consciousness, arising from our limited perspective. Emergence. Another leading view is that time is not fundamental but emergent. It arises from underlying quantum correlations, from the statistical behavior of countless particles, or from specific quantum dynamics and the process of thermalization, the movement towards thermodynamic equilibrium. In this view, time appears when complex systems like our universe begin to evolve and increase in entropy. It's a property of macroscopic systems, not a fundamental feature of the underlying quantum reality. Relational time, Rovelli's view. Building. On Leibniz's ideas, physicists like Carlo Rovelli propose that there is no absolute time in quantum gravity. Instead, time is only defined by the relationships and changes between quantum events. One system acts as a clock by virtue of its changing states, and other systems' evolution is measured relative to it. Non-commutative geometry. Alain Conné's work suggests that time could emerge from a deeper, non-commutative structure of spacetime, where the order of operations matters in a way that doesn't correspond to simple numbers. Loop quantum gravity. This theory, a leading contender for quantum gravity, posits that spacetime itself is granular, composed of discrete loops or networks. In some formulations, time isn't a fundamental dimension, but emerges from the dynamics of these quantum spatial loops. Causal set theory. This theory proposes that spacetime is not continuous, but a collection of discrete, causal sets of events, where only a partial order, which event can influence which other event, is fundamental, and time emerges from the statistical properties of these causal relations. The quantum realm forces us to confront the possibility that time, as we know it, might not be the ultimate truth, but rather a remarkably robust and useful approximation that helps us navigate our complex, macroscopic lives. It's a dizzying, humbling thought to consider that the very foundation of our existence, the endless march of moments, might be something far more fluid, probabilistic, and intricately intertwined with the deepest mysteries of the universe than we ever dared to imagine. It truly is the jazz improvisation of reality, constantly surprising, always profound, and forever beckoning us to understand its rhythm. The nature of time, present, past, future, and the philosophical depths after our journey through scientific time. It's time to pause and reflect on the deepest philosophical questions it provokes. What is time fundamentally? Is it a flow, a dimension, or an illusion? Philosophers have wrestled with these questions for millennia, often drawing on and sometimes challenging the scientific views of their day. One of the oldest and most profound debates in the philosophy of time centers on the reality of the past. Present and future, presentism. This view holds that only the present moment is real. The past was real, but it no longer exists. The future will be real, but it does not yet exist. Time is seen as a genuine flowing process, and the now is a uniquely privileged moment, constantly moving forward. This view aligns well with our intuitive experience of time as passing. However, it struggles to reconcile with special relativity, where there is no universal now across different inertial frames. If what is present depends on your motion, then a rigid universal present becomes problematic. Eternalism, or block. Universe theory. This view holds that past, present, and future are equally real and coexist as parts of a four-dimensional space-time block. Time is not a flowing entity, but a dimension, much like space. All events, from the Big Bang to the heat death of the universe, are laid out as fixed points in this unchanging block. Our perception of a flowing present is an illusion of consciousness, a way for our minds to process this fixed reality. This view is highly compatible with Einstein's theories of relativity, particularly the concept of spacetime, where all events are just coordinates in a single manifold. However, it raises deep questions about free will and the subjective experience of time's passage. If the future already exists in the block, how can our choices be free? Closely related to this debate is J.M.E. McTaggart's famous argument against the reality of time, 1908. McTaggart distinguished between two ways of ordering events, A-series. Events are ordered as past, present, and future. This series involves change, as an event shifts from future to present to past. This is the dynamic flowing aspect of time. B-series. Events are ordered simply as earlier than or later than. This series is static and unchanging, e.g., the Battle of Hastings was earlier than the invention of the Internet is always true. McTaggart argued that the A-series is essential for time's reality, as without change, there is no time. However, he also argued that the A-series is inherently contradictory and impossible, therefore concluding that time itself is unreal. While his argument has been widely debated and critiqued, it powerfully highlighted the profound difficulty of defining and understanding the nature of temporal passage. The very idea of an objective, unique now remains one of the deepest philosophical puzzles. The relationship between time and consciousness is another critical area. Our subjective experience of a now or a present moment is remarkably short, estimated to be around 2 to 3 seconds, the specious present. Beyond that, our perception is heavily influenced by memory and anticipation. Is consciousness simply an emergent property of complex physical systems that happens to organize information sequentially, creating the feeling of time's flow? Or is consciousness itself a fundamental aspect of reality, interacting with physical processes in a way that creates time's passage? This links back to the problem of time in quantum gravity. If time disappears at the fundamental level, perhaps it is precisely our conscious perception and the act of measurement that bring time into existence at our macroscopic scale. Finally, consider the link between time and information. Some theories propose that time can be viewed as a measure of information processing or creation. As entropy increases, new information is effectively generated, e.g., the specific arrangement of broken glass is information that didn't exist in the same way for the intact glass. In this view, time's flow is intrinsically linked to the universe's ongoing computation, its continuous act of becoming more complex and differentiated. Our very existence, as complex self-organizing systems, requires a directionality of time to process information, build memories, and evolve. So, is time a fundamental property of the universe, an emergent phenomenon, or even an illusion of our perception? The answer remains elusive, a tantalizing whisper at the edge of our understanding. Perhaps it is all of these things at once, depending on the scale and the lens through which we view it. The end. Or just the beginning? The ever-deepening enigma of time. And so here we are, having journeyed into the deepest, most intricate layers of time, its subjective experience, its meticulous measurement, its grand cosmic architecture, its perplexing quantum dance, and its profound philosophical implications. We've stretched our minds to grasp that time is not merely a uniform ticking clock, but a profoundly personal, elastic experience, shaped by our attention, our emotions, our memories, and the very wiring of our brains. We've marveled at humanity's relentless ingenuity, from rudimentary sundials to atomic clocks so precise they mark the imperceptible wiggles in space-time itself, revealing our deep drive to organize, predict, and control. And we've wrestled with Einstein's revolutionary insights, understanding that time is inextricably woven into the very fabric of space-time, bending with gravity, stretching with speed, shattering our notion of a universal now. The enigmatic arrow of time, the reason eggs don't spontaneously unscramble, finds its profound root in the universe's relentless, irreversible march toward increasing entropy, a cosmic drift towards greater disorder and statistical probability. And at the very frontiers of physics, in the quantum realm, time becomes even more elusive, a potential emergent property, a statistical phenomenon, or perhaps even an illusion that dissolves into a timeless quantum background. This problem of time challenges the very notion of a fundamental temporal dimension, suggesting that our experience of time might be a byproduct of our conscious interaction with reality. As we settle into the deep quiet of the night, perhaps, with these profound and beautiful thoughts gently swirling in your mind, remember that time is far more than just a measurement. It is a fundamental dimension of our existence, a silent partner in every breath we take, every dream we chase, and every precious memory we create. It is both the vast, unseen canvas upon which reality unfolds and the intricate, ever-changing brushstrokes that define our journey. Time is the very medium of change, the prerequisite for experience and the grand arbiter of all becoming. It is the framework for our consciousness, the stage for our stories, and the ultimate mystery that continues to challenge the sharpest minds. Thank you for joining me on this gentle, winding, and profoundly detailed journey through time. May your curiosity be satisfied, your thoughts slow and peaceful, and your dreams be wonderfully, timelessly vast. Sweet dreams, sleepy enigma. And as you drift off, perhaps ponder, if time truly is an illusion, what then is left? If the past and future already exist in a block universe, what does that mean for our choices? And if time is ultimately emergent from the quantum realm, what is the truly fundamental reality from which it springs? The universe, in its vastness, holds these secrets still.